Great. Today, I'm going to take time to talk about just one of the mission concepts that we considered as a part of our study. We first started with 4 different mission concepts under a flagship scope. And the one that we found the most compelling was Orbilander. So that's what I'm going to take the time to talk about today. Of course, I'm here representing a much larger team who've put in a lot of long hours and hard work into making this study possible. So on this first slide is the core science team who've done a fantastic job. And here is our broader team of collaborators. We were very fortunate to have so many people sign on and offer their assistance. This team represents a very broad representation in terms of discipline and also geographic location. So thanks to all of them for their inputs. And I'd also like to briefly thank many PIs of different tech development grants through programs like IC2 and Cold Tech, who were very generous in sharing information about the astrobiology technology that they are developing and that's coming online in the next decade. Finally, I'd like to thank the APL Mission Design Lab team led by Karen Kirby and Pete Greenhour with project science from Rob Gold. Obviously, without their expertise, this would not have been possible. All right, so I don't think I need to spend much time motivating why we need to go back to Enceladus. Cassini characterized Enceladus's subsurface ocean thanks to the plumes of material that are emanating from the South Pole. And from those data, we know that Enceladus's ocean seems to check the 3 requirements for habitability as we think of it. So the next question to ask at Enceladus really is whether or not that little moon's subsurface ocean is inhabited. So for the purpose of this study, what we're trying to do is provide the Decadal Survey Committee with a quantified understanding of the science return of Enceladus life detection, specifically in flagship class architectures, to give ourselves a better understanding of what it would take to do astrobiology at Enceladus. So that's where the Orbilander comes in, and I need to be very clear about this up front. We are talking about one spacecraft, which has 2 different phases. We have the orbital phase, where we spend about 1.5 years in orbit. Before building up data to convince ourselves we found a good landing site, and then we get ourselves down to the surface with the same spacecraft. Our payload includes 3 different instrument suites. We have the life detection suite, which I'm going to spend a lot of time talking about. Then we have the recon and remote sensing suite, which I don't have as much time to talk about, unfortunately, but it includes narrow and wide angle cameras, a laser altimeter, a radar sounder, and a thermal emission point spectrometer. For landing, we have the in situ suite, which consists of a camera for looking at different sampling sites and a seismometer. We're powered by 2 RTGs and a battery. The science goals for our study were primarily focused on the search for life. We thought that this was the primary science question to be answered at Enceladus with the next mission. We broke that down into looking for 5 different classes of biosignatures, looking for chemical biosignatures like amino acids, lipids, the different levels of complexity that we could detect with the survey of the different chemical compounds in the plume material. But then we also wanted to look at higher risk, higher reward biosignature detection strategies, like looking for a potential genetic polymer or polyelectrolyte and characterizing cell-like features. But critical to the search for life, especially at the scope of a flagship mission, are contextual measurements like the 2 I'm showing at the bottom of the pyramid here. We thought that determining the ejection mechanics, or the path that the plume particles take from the subsurface ocean up and through the vents, as well as a assessing the ocean habitability, kind of continuing what Cassini did at Enceladus, are really important measurements, science goals to address at Enceladus to really provide legs with which the search for life can stand on. That is for us, it was really important in this study to keep that context science and keep the scope of the missions broad enough to warrant, the flagship title. Unfortunately, I'm not going to spend as much time on those two pillars of our science goals, but I don't want you to take the time I spend on them in this presentation as a reflection of how much time we spent on them in the process. So the search for life science objectives that we created translated into a life detection suite payload of 6 different instruments. We have the high resolution mass spectrometer, a separation capable mass spectrometer, ion selective electrodes, microcapillary electrophoresis, a microscope, and a nanopore. This instrument suite combines instruments of pretty high TRL, things that have flown before, the mass spectrometers and the ISE, while also including things that are currently in development, bringing them up to levels like TRL 5 and 6, thanks to programs like IC2 and Coltech, and that includes the microfluidic electrophoresis device, as well as the microscope. And then the nanopore is at much lower technology readiness level, but the power of the data that it would provide really convinced us that it was worth pursuing in this life detection suite for our concept. So you might take a look at that payload and say, well, Shannon, there are a lot of instruments that have overlapping capabilities there. And we did that strategically. So in this graphic, I took from the Ladder of Life paper by Marc Naveau, and it shows some of the different biological features or the features of life that one might go after. Given that we are studying flagship class architectures, we wanted to make sure both that we had complementary and orthogonal approaches and approaches that were more robust. So on the right-hand side, I'm showing our different instruments and what biological features our measurements would get at. So we're thinking that this combination would provide a very meaningful data set for the search for life. Once we had our payload, we wanted to think about how much sample we would need to make each of those measurements. So we did a very similar strategy to the Europa lander SDT, where we started with an assumption about the total organic content in Enceladus's ocean. Tried to take a more conservative value of 30 micromolar, and then we took that value and applied terrestrial ratios for our target biosignatures like amino acids and lipids and the free DNA in terrestrial oceans. Cell density was a number that we deviated a little bit more from the Europa lander SDT. Enceladus and Europa are different bodies, so perhaps that's not surprising. But we wanted to be conservative while also reflecting some of the estimates that have been put out there in the literature, which are as high as 100 cells per microliter in Enceladus's plumes. So with those assumptions about the biomass available in the plume, we then folded in the instrument requirements, like how much volume is needed for each measurement, and that gave us a total plume material that we needed to accumulate in order to do these measurements several times. Now, at Enceladus, we don't have to go down to the ocean for those samples. We can access the plume. And we like to think about the plume as offering 4 different reservoirs. So at the very top is the mixed plume. So above, say, 40 kilometers, the jets have dispersed. And so you have a higher likelihood of running into those vapor molecules and sampling them. but your particle sizes are much smaller, on the order of nanometers. If you go lower into the plume, now you have more collimated jets. So vapor sampling might be a little more difficult, but you get larger particles. And then if you're on the surface, you can get even larger particles that don't have, that are too massive to reach higher into the plume. And by catching them before they hit the surface, you can be assured that they are fresh. Of course, if you are interested in much larger volumes, then maybe you decide to access those surface deposits, with the possible caveat that they could be modified by processes like sintering or weathering. So our Orbilander concept gets at these 4 different reservoirs with 2 kinds of sampling mechanisms. First is the passive. So up in the orange cone and the orange box, I'm showing the 1 meter square funnel for collecting plume particles. And we also have a gas inlet so that we can sample that vapor. Once you're on the surface, we use that same funnel for catching plume particles. And then we also have an active mechanism on the surface for excavating surface material. For the purpose of this study, we are assuming a scoop, but I think it would behoove us if we went forward with an Enceladus, with a return to Enceladus, to have some dedicated study into what kind of sampling mechanism would be best for this body that is so tiny and so cold. Maybe something more akin to Dragonfly with a vacuum and a drill, or something that has rasps, for example. Okay, so now that we know how much sample we need and how we're going to get it, we can start to build our concept of operations based on how long we think it's going to take to build up that sample. On the right-hand side, I'm showing which values we assumed for sample flux. Again, we tried to take more conservative values from what's available in the literature, but not so conservative that we were pessimistic. On the left-hand side, I'm showing the amount of sample required for, in blue, most of our life detection suite, and then in gray, the nanopore. You'll notice right away that the nanopore requires a lot of sample, much more than you can possibly build up according to our assumptions while in orbit. So the nanopore, we decided, was not something that we would run in orbit. And the other life detection suite measurements we would probably only run once in orbit before we got down to the ground. So with those drivers of our timeline drivers from sample requirements in mind, we started building the orbital phase of our mission. We are in a halo orbit around Enceladus with a period of about 12 hours. Most of the orbit is actually spent doing communications or station keeping maneuvers or observations. And then once we get down below about 100 kilometers, we start doing our primary science. And our periapsis oscillates between 20 and 70 kilometers. While in orbit, we are mostly taking landing site reconnaissance data while we are building up enough sample to run the life detection suite. So every time we run through the plume, our collection devices are open and collecting sample. And once we've accumulated enough, then we can begin to run the analyses. The vapor sampling happens independently because the mass spectrometer is a little more power hungry. And it's with that direct gas inlet, we don't have to worry so much about building up sample. And we also are, in addition to doing the landing site recon, which we do with the narrow and wide angle camera, the laser altimeter, and the thermal emission spectrometer, we're also conducting radar sounding flybys as well. So what's exciting is that even though it takes a while to build up enough sample, we think that we can build up enough sample to run through the almost complete life detection suite, with the exception of the nanopore, by day 200. which is less than half of our 1.5 years in orbit that we are planning to do. So if time allows, we can do more life detection measurements in orbit. There's a lot of schedule flexibility built into this mission concept. Once we find a landing site that we like and we get down to the ground, we begin the landed phase. Very similar concept of operations here, just with much longer cadence. So the first thing that we do is start checking out our instruments. We deploy our seismometer. We start looking around for where we might want to do the scoop. And then we begin seismic monitoring. But while we're doing all of that, we're again accumulating a bunch of sample from plume fallout with our passive collecting device. So within the first month, we do our first life detection suite analysis on the surface from what the funnel collected. We take a break to do some imaging to allow ourselves to build up more sample, to spend time sending the data back, and to clean out the life detection suite system. And then we run another suite of life detection analyses with the passive sample, this time with the nanopore. And that repeats, switching to the active mode where we're using a scoop until after 150 days, we've done 5 full sequences of the life detection suite with passive and active samples. Again, that's leaving us a lot of schedule margin to handle if we want to do even more analyses, or to if our data return rate isn't as good as we want it to be. We've got a lot of schedule margin. So to summarize the two different phases, again, one spacecraft that we're taking data, that we're sending in orbit, taking data, then we get ourselves down to the surface and land and do the life detection suite measurements from the ground. This ability of the single spacecraft to get at those 4 different reservoirs with multiple measurements was a pretty compelling case, we thought. This makes the Orbi-lander resilient to our uncertainty in the biomass that's in the plume, so that those assumptions I showed at the beginning of 1.6 microliters per meter square, if the value of the organic content is much lower than that, we have some resiliency to that. To wrap our brains around that, Marc Neveu, have to give him credit for this beautiful figure. It's a little complicated though, so I'd like to step us all through it. We made an assumption about the number of microbial cells per milliliter in the Enceladus plume material. That's this 10 to the 3 number. We had to pick a number because we are designing a mission concept, but in reality, there's a vast uncertainty in what the actual number of microbial cells in a sample would be. And the breadth of uncertainty stems from 2 different camps. One is our uncertainty in the energy supply that Enceladus can provide. So how much biomass can Enceladus actually support? And on the other side, we don't really understand how much energy is required by biomass. So, so there's a very large uncertainty here behind our assumptions. But we have a life detection suite that has kind of finite expectations for how much sample volume is necessary to run different analyses. And before I move into comparing the different phases of our mission, I want to make sure that this white line is clear. This axis is going to shift left or right relative to the green one based on your life detection suite. So if you're carrying more instruments that require smaller sample volumes, you might be able to get away with lower amounts of sample collected and analyzed. Of course, there is a limit to how much sample could possibly be processed in a finite amount of time in a typical mission duration. So probably, even if you needed 3,000 liters, you wouldn't be able to scoop it up and pass it through your system in a reasonable amount of time. But for our landed and orbital phases, we have an estimate of how much sample we need and can accumulate, and that's shown here. So the orbiter accumulates much less sample than can be on the ground based on our assumptions of what biomass is in the plume. Just for context, the Europa lander SDT assumed a more conservative value of the number of microbial cells. And over here, we're showing just how much material you would get through multiple flybys of Enceladus. Again, that's not saying that you absolutely need these larger volumes, but the life detection suite that we have put together requires larger volumes than what you would accumulate with multiple flybys. So with the geochemistry results, we might hope to collapse some of the uncertainty in that energy supply that Enceladus can provide. That still leaves us with 6 orders of magnitude of uncertainty in what cells actually need, but it allows us to be a little bit more robust in the results that we interpret from our life detection suite. So these blue bars down here are showing that collapse of the uncertainty down to the biological rather than the environmental uncertainty. So now in purple here, we're showing different kind of possible results with our astrobiology mission. And just to take you through, if with the orbiter, for example, if we got lucky and we saw with all 5 of our biosignature objectives, signs of life, cool, Enceladus is inhabited. But let's say we didn't. With the geochemistry, we can start to parse that result. Is it just that we have not collected enough sample with our orbital phase, or is it actually that Enceladus is uninhabited? So you can begin to ask those secondary questions with more and more sample that you accumulate. So to wrap it up, I think that the search for life at Enceladus represents a very compelling investigation and can be done in the next decade. Enceladus's plumes offer a unique opportunity for acquiring large sample volumes of oceanic material. You can do this both in orbit and on the surface, and as our study has shown, you can do that with 1 spacecraft at Enceladus. Our Orbilander concept is flagship class, and we think that it addresses a flagship scope science as well, addressing astrobiology, geophysics, and geochemistry questions. And finally, this study and any potential future missions to do astrobiology at Enceladus are going to require continued support of biosignature detection, sample preparation, sample collection, and contamination prevention technologies. We've already made use just in this study from the results of IC2, Coldtech, and those kinds of programs. So continued development is critical to the success of astrobiology missions in the next decade. With that, I'd like to thank you for taking the time to listen to our mission concept and encourage you to take a look at our report, which will detail both the Orbilander and also talk more about the other different architectures that we considered but decided were less compelling than the Orbilander concept. Thanks.
Great, thanks so much, Shannon. We will go ahead. We have quite a few questions, so I'll go ahead and relay those to you. So I'm going to go ahead and skip the first question in our Google Doc sheet because that was, I think, already addressed in Shannon's talk as it was written earlier. So I'll go to the next question, which is from Kirby Runyon at APL. What is the Hill sphere of Enceladus? 12-hour orbit seems a 12-hour orbit seems like it would be perturbed by Saturn.
Well, I have to say I don't know the Hill sphere of Enceladus off the top of my head, but our orbit is unstable over the long term, which is why we are carrying the capability to do station keeping maneuvers. That's a critical part of making sure that we are staying in orbit and crossing over the right areas of the surface to do our landing site search.
Great. Next question. Looks like maybe it was already answered. So I do apologize to Mark Bullock for someone leaving your question, but it looks like the answer is in the comments. So I'll go ahead and jump down to Mohammed's question from UT Austin, which is how feasible is catching a rock piece in terms of rock size estimation and motion of the collecting device?
How feasible is catching a rock? Was that the question, Becky?
Yes. Yeah. How feasible would it be to catch a rock in terms of, you know, it says rock size estimation and motion of the collecting device. So I think the question is, you know, what are the chances that you would end up catching a rock based off of the estimated size of a rock particle?
Well, we think that the particles coming out are going to be on the upper end of millimeters. That should be intercepted by our funnel. The rate at which, of course, depends on where we end up landing and the distance to the vents. So if you're getting closer, you're going to get larger particles, but we don't want to get too close because that might be too warm or too topographic for our direct to Earth strategy. Once we are on the ground, we are on the ground and we are not mobile. So we'll rely upon that funnel to do the catching for us.
Okay, so next question is from Sam Howell at JPL. What is the trade in delta V mass to achieve the orbit? Do you lose time in the grunt or payload? And is there a middle ground?
I'll leave the detailed numbers to the online response, but in order to achieve the Enceladus orbit, we actually have to spend quite a few years doing a moon tour where we pump our orbit down from Saturn orbit into Enceladus orbit. That allows us to deliver our payload into Enceladus orbit. But as I mentioned before, it is unstable, so we have to do some station keeping maneuvers.
Okay, so the next question we have, how much sensitivity to depth and seismic activity types are anticipated for the seismometer's frequency range?
So we took the assumptions of the Europa lander science definition team for our seismometer. Obviously, the exact seismometer and frequency range that you would want at Enceladus is going to be a little bit different and would warrant a more dedicated study since Enceladus's environment is different than Europa.
Okay, looks like maybe the next question got removed, but I'll go ahead and jump down. So Erica Nathan from Brown University asks, what are the landing site requirements for the lander, both in terms of proximity to plumes and hazard avoidance? How likely is it that reconnaissance from the orbiter will find such a site in the SPT, or is there a contingency plan if a suitable site is not found in the SPT?
That's a great question. We spend a lot of time thinking about what the criteria should be for landing site selection, and I realized that it says 4 there, and I've listed 6, so apologies for the typo. First, we have to make sure that we are landing in an area that receives some sunlight so that we can do our direct-to-Earth communications. We are also looking for areas that have low but non-zero boulder count. This is to help convince us that we're not going to land in a thick pile of fluff. You might have noticed that there are some skids or some skid feet on the lander legs. That helps us distribute our mass, but we, again, just want to be sure that we're not landing into some big snow pile. For the direct-to-Earth and also to avoid tip over, we need to be sure that we're not on high slopes and that we're not in a valley. But we also want to make sure that we're not anywhere too warm, so we don't want to be directly on a vent. And then we also want to consider, as the questioner mentioned, the fallout rate. The fallout rates are modeled to peak out on the order of 1 millimeter per year, very close to the plumes. Our schedule is robust to fallout rates as low as 1/100th of that. So that gives us a pretty large area to work with in terms of the fallout rate. The ultimate mitigation, of course, is having that active sampling mechanism, because even if we can't catch something from the sky, we can scoop it from down below. That just introduces some uncertainties in your results because we're not sure how long that material has been sitting on the surface. So how representative it is of the plume then would be a matter of, I'm sure, much debate.
Okay, so I'm going to go ahead and jump down a couple questions because it looks like some were answered online. So do you anticipate carrying a very broadband seismometer similar to InSight, a short period instrument, or multiple seismometers?
We are only carrying one seismometer. We do have a lot of time at our one location on the ground. As to whether we would do long period or short period, I think in one of Steve Vance's papers, he advocates for the short period. But again, that would be something that we would want to take a look at at a higher fidelity in a higher fidelity study.
Okay. Does the orbital sorry, I'm allergic to ground early. I messed that up. Does the orbital speed run the risk of breaking apart or contaminating the samples collected by the funnel? Can you make firm conclusions about content from sample fragments only?
Sorry, I missed the first part. Does the orbital?
Yeah, sorry. I'm sorry. Are you having trouble hearing me? Does the orbital speed run the risk of breaking apart or contaminating the samples collected
the velocity.
by the funnel?
Got it. Thanks.
Yes.
I kept hearing feet. The maximum velocities that we would be sampling at are on the order of 200 meters per second. So that allows us to get very low relative velocity to the plume particles themselves. So we don't anticipate having any kind of breakup of the particles in the same way that Cassini had to deal with.
Okay, so that is all the questions that didn't have an answer already, but I'll give you an opportunity to maybe speak to a couple that are being answered in the doc, just in case you want to elaborate anymore. So what about light element isotope abundances, such as oxygen, carbon, sulfur? These could be highly complementary to the life detection experiment.
Yes, isotopes were a topic of great interest in our science team discussions. Things that we can get with the high resolution mass spectrometer are on our STM as target measurements. We also spent some time thinking about being able to do compound-specific isotopic measurements, and we were really excited about doing those, but the technology to our understanding, just isn't there yet, and is something that we hope gets continued development, because that allows you to take your amino acid measurements, for example, to a higher level of fidelity if you're able to also do isotopic measurements.
Okay, and then there's a question here about potentially including a magnetometer on the strawman payload. It would strongly support, for low resources, the science objectives of geological context and ejection mechanisms. One of your team members answered that, but would you like to maybe add some more thoughts?
Well, my first response would be that I think I can speak safely for the full science team that we want to be sure that it's clear that this is an option. Obviously, that's not the only way that you could return to Enceladus, even not the only payload that you could include on an Orbilander. Some of the difficulties with including a magnetometer might be the length of the boom and making sure that we can retract it for a safe landing. But unfortunately, we can't include everything.
Wouldn't it be nice if we could? Okay,
yes.
I'll just do these last two that were already answered in the document, but maybe you can elaborate. So Kenda Lynch asks, what are the constituents that will be measured by ISEs? Are reactive oxygen species and chlorine oxyanions being targeted?
Yes.
Okay, and then the last question, what is the major sampling advantage of landing a spacecraft when there is plenty of material flying out of the plumes? Is it avoiding the destruction of samples as they collide with the orbiter?
This is a great question. Let me go back to my diagram here. The plume is not the same throughout the different altitudes. As you get to lower altitudes, you have access to particles that are larger and therefore don't have enough energy to make it higher into the plume. So those larger particles, based on our sampling with Cassini, might have a higher organic content. So they're of high interest, and you really can't get the largest particles from the plume. You have to be sitting on the surface. Maybe that's enough. Maybe it's enough to just sample in the plume. We just don't know.
Okay, and then we have one more late edition question. How does the geologic history of Enceladus, in particular the evolution of the ocean and hydrothermal system, influence your expectations of what you might find?
That's a great question. That goes into our uncertainty in the biomass that we anticipate being available in the plume. There aren't great constraints on the history of Enceladus, and that's one of the driving reasons we wanted to include context measurements, like on looking for different geochemical signatures in the plume. Because that's going to drive or help collapse our uncertainty in how much energy the Enceladus system can provide now. Getting at the past is a little bit more difficult, but certainly more data would help.